In this final video of this 3-video series on producing and solving recurrence relations, we'll talk about two additional methods, one of which involves recursion trees and yields an iterative solution, and the other which depends on a theorem called the master theorem. And we'll see also a form of the master theorem that is simpler, applies to some cases, but not all cases to which the master theorem applies. The first of the two methods that for solving recurrence equations that we're going to talk about is sometimes called the iteration method, or sometimes called the recursion tree method. It involves iteratively expanding the recurrence as the size of the divisions become smaller and smaller. And on the basis of that, to express the overall time t of n as a summation of terms that depend on n. So the key is to focus on how many times the recurrence needs to be iterated to reach the boundary condition. In merge sort, the boundary condition was the subfile size is 1. In other cases, the boundary condition is the subfile size is less than some constant. The second parameter is for each level of that iteration process, we get a term and we sum over the levels to get the overall time. This produces a summation formula, and then we need to use that summation formula to get the final solution theta t of n equals theta of some function of n. Please do not confuse this iterative methods for solving recurrence equations with methods for solving iterative, for evaluating iterative methods. But now, let's use this example for this recurrence relation. T of n equals 3t of n over 4 plus n. Well, we'll put the t on the right side, so it's n plus 3t of n over 4. But we have an equation for t of n over 4 by plugging n over 4 into the right side. And so we get n plus 3 times our t of n over 4, but t of n over 4 is n over 4 plus 3t of n over 4 over 4. That is to say, n over 16. So now we've got t of n in terms of n plus 3n over 4 and 3t of n over 16. Now we play the game again, we iterate. So we go down one more level, another division by 4. We plug n over 16 into the left side of the original recurrence relation, t of n equals 3t of n over 4. And so we get, okay, so I first simplified the previous one, which gives me n plus 3 times n over 4 plus 9t n over 16. And then when I plug the t n over 16 formula up here into the first equation, we put n over 16, and so this becomes n over 64. We get a 27 n over 64, and you get 9 times n over 16. That comes from the first term. this n, and then you get, because of 3 times 3, and then you get another 3 times n over 64, and so on down the line, okay? So we can sort of, this is the basic idea, that we're continually plugging in the original equation for the right side. And so what we get is, out of that, t of n plus 3n over 4 plus 9n over 16 plus 27n over 64. And when we get down to log to the 4 of n being our threshold or our constant, we have found that we've gone down that many levels. We have 3 to that power times theta of 1. And that's a summation, n times the sum of I times 3/4 to the I, plus some theta of 3 to the log 4 of n, but that's the same as n to the log 4 of 3. And so we have a sum of 2 terms, both of which we can evaluate. One is n times a summation, and we'll see the summation gives us a formula. I mean, summation gives us is a formula that we can show is bounded by a constant. So we have a constant times n plus theta of n to the log base 4 of 3. Oh, log base 4 of 3 is less than 1. So we have n to a power less than 1, theta of that, plus a constant times n. Ooh, the method is order n. Got that? Be careful. This idea of taking something to the something power, 3 to the log 4 of n, and turning it around because to the equivalent form of the exponent to the other guy's power, is, sorry, not the exponent, but the log operand to the other log of the other guy, is a standard identity that you need to be comfortable in using. So this produces 4n plus omega of n, and then that says it's theta of n. Okay? So this is the basic idea. It's easier to do when you put everything in the form of a tree. And the idea of the tree is the levels of the tree are different. You move from one level to the next when you have to reapply the divide and conquer step. And it allows you to visualize and organize the bookkeeping. So let's look at our merge sort. Our merge sort at level 1 takes n times to merge the 2 sublists, plus the application first to one sublist and the other sublist. That is to say, it's n plus t of n over 2 plus t of n over 2. Now, at this next level, the n over 2 takes n over 2 takes n over 2 time to merge, plus move down a level, t of n over 4 plus t of n over 4. And this n over 2 likewise requires an n over 2 to merge plus t of n over 4 plus t of n over 4. And we play the game over and over for log n steps down this tree. And then we look at the total time at every level. So total time at the top level is n. The total time at level 2 is n over 2 plus n over 2, which is n. The total time at level 2 levels down is n over 4 plus n over 4 plus n over 4 plus n over 4, which is n. And we have log n such levels, each taking time n, and therefore merge sort is order n log n. The solution to this recurrence relation that we promised would be order n log n really is order n log n by this analysis via a recursion tree. Even if we don't have an algorithm, but we have a recursion tree that comes from a recurrence relation, we can do the same thing. So T of n equals 2Tn over 2 plus n squared, let's say. So now, instead of order n time at each step, we have order n squared time. Okay, so we have n squared as the time we have to do the apply our recurrence relation at the first step for the combined part, if you will. So it's n squared for the combined. And then we have 2t of n over 2, so we'll write them down here, t of n over 2, and t of n over 2, one level below. And now t of n over 2 is going to take n over 2 squared here for this one, and n over 2 squared for this for the right hand one, and then they call t over n over 4 and t over n over 4 and t over n over 4 and t of n over 4 at level 2. When we finish producing the tree, we see that there are log n levels, and at the top level there's a single entry of n squared, and so we put n squared. The second level, there are two entries that have, the left one's n squared over 4, the right one is n squared over 4. The sum of those two is n squared over 2. And we put that's the total time to work at that second level. At the third level, we have n over 4 squared 4 times. That is to say, we have 4 times n over 4 squared, which is n squared over 4. And you can see that the next level will be n squared over 16, n squared over 8, and then the level after that, n squared over 16, and so on. And so summing over all the levels, if we had an infinite number of levels, it would be 1 plus a half plus a quarter plus an eighth plus continuing on forever times n squared. And the sum of that sum is 2. So when we cut off the sum, it's less bounded by 2, so that the sum of the coefficients of n squared is bounded by a constant, and as a result, the overall sum is theta of n squared. Example, t of n equals t of n over 3 plus t of 2n over 3 plus n. So now the division is not into equal size subgroups, but into a third and the other 2/3 the size. And the combined work is order n. So our tree has n at the top and n over 3 and 2n over 3 at the next level. Moreover, the n over 3 divides into a third and a 2/3 of it at the next level, so you get n over 9, a third of n over 3, and 2n over 9, 2/3 of n over 3. And in regard to the right term at the second level, it divides into 2/3 of 2n over 3 and 1/3 of 2n over 3, so we get 2n over 9 and 4n over 9. Looking at the top level, there's one element. The total time there is n. At the second level, we have n over 3 time plus 2n over 3 time. n over 3 plus 2n over 3 is n. At the next level, we have n over 9, 2n over 9, 2n over 9, and 4n over 9, which gives you 9n over 9. And that's n also. And so for each of the levels, which are as many of them as log to the base 3/2 of n. 3/2 because the second term only divides by 2/3 every time. You get number of levels, log base 3/2 of n, times n. But log of anything, log base anything of n, is just log of n for any other base. So the overall solution is theta of n log n. Okay, so that was the third simplification method, the recursion tree method that yields an iteration or a summation, if you will, and then you can evaluate those sums. Here is another of the simplification methods. Remember we talked about simplification of throwing away negligible things in the arguments? And we also talked about simplification by throwing away ceilings and floors. Here's another simplification method that works and that makes your life easy. So let's take that same recurrence relation that we solved a moment ago using the recursion tree. T of n equals T of n over 3 plus T of 2n over 3 plus n. The trick is to look at the two arguments, n over 3 and 2n over 3, and replace each of them by their average. So the average of n over 3 and 2n over 3 is n over 2. And so if we replace them, we get T of n over 2 plus T of n over 2 plus n. Right? This simplification has allowed us to have both of them have the same argument, namely the average argument. And when we rewrite that, we see that's T of n equals 2T of n over 2 plus n. Long since we have seen that the solution to that is theta of n log n. And so the original recurrence is solved by theta of n log n. Okay? This simplification method, by the way, is not in the book, but it's a good one to use. Now, sometimes the t's on the right side not only have different arguments, but they're not multiplied each by 1, but by different constants. Here is the recurrence T of n equals 2T of n over 3 plus T of 2n over 3 plus n. So the first term on the right is multiplied by the constant 2 and the other one by 1. As a result of that, we need to do a weighted average using the coefficients as weights. So we have weight 2 and weight 1. Total weights is 2 plus 1 is 3. And so we multiply the n over 3 with weight 2 to get 2n over 3, and the 2n over 3 with weight 1 to get 2n over 3. We sum those to get 4n over 3, and we divide by the sum of the weights 3, and we get 4n over 9. That's our weighted average, and then we plug in the weighted average in both places. And so then we get T of n equals 2T of 4n over 9 plus T of 4n over 9. That's 3T of 4n over 9. And so we've replaced the original recurrence by T of n equals 3T of 4n over 9 plus n. And then we need to solve that recurrence. And that one will easily submit to the next method we're going to talk about, which is using a master theorem. So here are some worksheet questions that you need to answer and pass in. And here is a pair of exercises that you'll do in our inverted class with the help of the LAs and me and the TAs. We come to our final method. There is a theorem that we will not prove here in the class, but only quote. And the idea is we can use that. And the basic idea is if we have a recurrence relation of the form T of n equals a, some constant a, times T over n over b, where b is a constant, plus some function of n, and if f of n is asymptotically positive, and T of n is defined for all integers, non-negative integers, and n over b is actually an integer which is either the floor or the ceiling of n over b, but that's okay. We know how to ignore that. If we have that, and if the a and the b and the f of n satisfy certain constraints that we'll talk about, then the master method tells us what the solution is. So the master method is a little bit complicated in its original form. If there exists some constant epsilon, and f of n is order big O, is in the set big O of n to the power log sub b of a minus epsilon, then here comes the solution. T of n is theta n to the log sub b of a. Okay, so that's one. If f of n doesn't involve that epsilon, it's simply theta of n to the log sub b of a. It's theta of that. Then T of n, we know the solution. It's n to the log sub b of a times log of n. Just a formula. And if f of n is in omega of n to the log sub b of a plus some positive epsilon, and here's an important and it's the case that f of a times f of n over b is less than or equal to c of f of n for some positive constant greater than 1, and all sufficiently large n, then T of n is of the form theta of f of n itself. Okay, so that's three reasonably complicated relationships. One that applies if f of n has this property, one that applies if f of n has the second property, and one of which if f of n has the third property and there's an additional constraint that's satisfied. We'll see an example shortly of that. But there's a particular case that makes this whole thing a lot simpler, and that's when f of n is some constant times some power of n. When the function f of n, when T of n is a times T of n over b plus f of n, when that function f of n is simply some power of n, the master theorem is much simpler. And this works for any power of n. N to the 0, in other words, a T n over b plus c, because n to the 0 is 1. N to the 1, that is to say, where f of n is c, is cn. n squared, but also n to the 1.439, any power of n. If you look at the recurrence relation, it involves an a constant a, a constant b, a constant c, and a constant k, and the c is irrelevant. All the conditions and results have to do with a, b, and k. So you give me a recurrence relation, and you know a, b, and k. You need to compare a to the kth power of b. If a is larger than the kth power of b, then t of n is solved as theta of some power of n, and the power is the log base b of a. If a is equal to b to the k, then t of a is theta of n to the k log n. And if a is less than b to the k, t of n is of the form theta of n to the k. So let's consider some examples of those rules. Our first example is the recurrence relation t of n equals 16 t of n over 4 plus n. And we want to solve that recurrence relation. Here, a equals 16, b is 4, and k equals 1. That is to say, the n to the k at the end is n to the 1 is n. So we're supposed to compare 16a to 4 to the 1 to 4. 16 is greater than 4, and so we're in case 1 of the theorem. And so the solution is t of n is theta of n to the log sub b of a, that is to say, theta of n to the log sub 4 of 16, since b is 4 and a is 16. Log sub 4 of 16, well, 16 is 4 squared, so log sub 4 of 16 is 2, and therefore the solution, t of n, is theta of n to the 2, that is to say, theta of n squared. Now let's look at another example. T of n equals t of 3n over 7 plus 1. In this case, a is 1, b is 7/3, because it's t of n over something, so 1 over 3/7 is 7/3. And k is 0, because we have n to the 0, which is 1, as the term outside of the t. So now we compare a, which is 1, to 7/3 to the 0. 7/3 to 0 is 1, so a is equal to b to the 0, and that's case 2. And so the solution rule from case 2 is t of n equals theta of n to the k log n. But here k is 0, so it's n to the 0 log n. That is to say, the solution is theta of log n. So we are not proving the master theorem, but we can use it very frequently. And indeed, you could use it for the case n equals 2, b equals 2, and k equals 1. In which case, you'd be comparing comparing 2, a equals 2, to 2 to the 1, which is the equality case, and you will see that the solution is theta of n log n. We long since knew that, like for merge sort, t of n is 2 t of n over 2 plus n. Now, if you don't have n to the k on the right side of the recurrence relation, but something more complicated, such as n log n, the simplified master theorem doesn't apply. And so we have to appeal back to the full master theorem that's more complicated. We still have an a or a b, but now we have an f of n, which is n log n. So in this example, t of n equals 3tn over 4 plus n log n, f of n is n log n, a equals 3, and b equals 4. The requirement is to compare n log n to either big O or big omega of n to the log base b of a plus epsilon. You can show that n log n is indeed omega of that for some epsilon. There is an additional requirement, however, and that is that the t on the right side, the term involving t on the right side, evaluated at its argument. So 3 times n over 4 times log t of n over 4 when f of n is n log n, that satisfies a particular condition and the condition is that it has to be less than or equal to the function itself, the n log n. Having satisfied that criterion, we're in case 3. Case 3 says that t of n is theta of f of n, and thus that recurrence that we're solving, t of n equals 3t of n over 4 plus n log n, is theta of n log n, theta of f. A slight change in that recurrence relation has the denominator of n be 3 rather than 4. So a equals 3, b equals 3, and f of n is still n log n. We still have the property of f of n being asymptotically larger than n to the log sub b of a. That is to say, being in that omega set. But here it's not polynomially larger. Put another way, the C condition doesn't hold. C becomes 1 rather than 3/4, and 1 is not less than 1. And so the master theorem doesn't apply, and you don't have an ability to use the master theorem to prove that recurrence relation, to solve that recurrence relation.
So here's a worksheet question. And here are some exercises that you'll do in class.
This is the end of the 3rd video, and indeed the end of the series of lectures on producing and solving recurrence relations.